Most people think salt actively melts ice, as if it breaks down the solid structure. But the truth is far more subtle, and it's a lesson in how easily our intuition can mislead us. Even something as simple as ice and salt reveals deep principles of physics that govern the world. Principles that Richard Feynman loved to explore because they challenge common assumptions. When salt is added to ice, the ice appears to dissolve faster. Roads clear more quickly in winter. Sidewalks become less slippery, and puddles form more readily. It seems obvious salt melts ice. But if we look closer, we realize that salt does not attack the ice directly. Instead, it interacts with a thin layer of water molecules that exists naturally on the surface of ice. Even at temperatures below freezing, the surface of ice is never perfectly solid. The molecules at the edges of the lattice are looser and more mobile. When salt touches this layer, it dissolves into it, creating a saltwater solution. This solution has a lower freezing point than pure water. In other words, water mixed with salt can remain liquid at temperatures where pure water would immediately freeze. This phenomenon, called freezing point depression, is a basic principle of chemistry and thermodynamics. It explains why roads salted in winter can remain clear, why salted ice melts faster than unsalted ice under certain conditions, and why, paradoxically, salt has no effect if the ice is extremely cold. Below a certain temperature, around 21 degrees Celsius for sodium chloride, the ice won't melt at all, no matter how much salt you sprinkle. The salt itself is not magical. It simply shifts the balance of energy at the interface between ice and water, making it easier for the surface molecules to break free and become liquid. This is where our intuition fails. Our senses tell us one thing, ice disappears, but what is actually happening is far more complex. The visible melting is a surface phenomenon driven by molecular motion and energy exchange. It depends on microscopic interactions between water molecules and dissolved ions. We cannot see these interactions with the naked eye, so our minds fill in the gaps with an oversimplified explanation: salt melts ice. Feynman often emphasized that understanding comes not from memorizing rules, but from seeing the underlying mechanisms, even in phenomena that seem trivial. We can also approach it through a simple analogy. Imagine sugar dissolving in iced tea. The sugar does not change the temperature of the tea, nor does it force the ice to melt. Instead, it alters the properties of the liquid, affecting how molecules move and interact. Similarly, salt changes the conditions for water molecules at the ice surface. The ice only melts faster when the surrounding environment allows it. This distinction between appearance and mechanism is critical in physics. It teaches us humility, showing that even everyday experiences can hide rich, subtle truths about the natural world. To understand why salt seems to melt ice, we need to look closer at the microscopic interactions that govern the process. Water molecules in ice are arranged in a rigid crystal lattice, each molecule bound to its neighbors by hydrogen bonds. At the surface, however, these bonds are weaker and some molecules are constantly jiggling, sometimes breaking free for brief moments. This thin layer of mobile molecules exists even below the freezing point, and it is what allows salt to have an effect. When salt is sprinkled on ice, it dissolves into this surface layer, creating a solution with a lower freezing point than the surrounding ice. This means the surface layer can remain liquid at temperatures where pure water would remain solid. This effect is called freezing point depression, and it is a direct consequence of how solute particles disrupt the order of water molecules. Each dissolved ion interferes with the ability of water molecules to align into a solid lattice, so the liquid state is stabilized at lower temperatures. This explains why salted ice appears to melt faster. The surface water does not refreeze as quickly, allowing more ice to transition into liquid over time. The bulk ice is not being attacked or broken down by the salt. Rather, the conditions for melting have subtly shifted. The energy balance at the interface between solid and liquid favors a slightly larger fraction of water molecules escaping into the liquid phase. Humans struggle to fully grasp this, because our intuition is based on macroscopic appearances. We see ice disappearing and immediately attribute it to the salt melting. Our brains are wired to look for simple cause and affect relationships, but nature often operates in ways that are more nuanced. The melting is not caused by the salt itself, but by the way salt alters the energy landscape at the molecular level. Even temperature fluctuations, impurities, and microscopic variations in the ice surface can influence how quickly ice melts. Physics provides the framework to understand these subtleties, but it requires moving beyond what is immediately visible. A simple thought experiment helps clarify the concept. Imagine a frozen pond on a winter morning. You sprinkle salt on the surface expecting instant puddles, but the temperature drops far below zero. Nothing happens. The salt has not failed. Rather, the freezing point depression is insufficient to keep water liquid under such extreme conditions. The melting process is entirely dependent on the interplay between temperature, molecular motion, and the presence of solute. This demonstrates how even a familiar phenomenon depends on precise physical laws that operate beneath the level of our perception. Feynman emphasized that the true joy of science lies in uncovering these hidden layers. He would argue that the apparent simplicity of ice and salt is deceptive. It is precisely these everyday experiments that reveal the richness of the natural world. By studying what we observe and questioning what seems obvious, we gain insight into fundamental principles. The interactions at the ice surface, the behavior of water molecules, and the influence of solutes teach us about energy, order, and probability. Understanding these details not only explains a common phenomenon, but also reshapes how we interpret reality, showing that what seems ordinary can hold extraordinary complexity. The process of ice melting with salt also teaches us something profound about observation and measurement. When we sprinkle salt on ice, we see the solid disappear, yet the microscopic reality is far more complex than our senses suggest. Each water molecule at the ice surface is constantly vibrating, occasionally breaking free from the rigid lattice. Salt ions interact with these surface molecules, subtly changing the probability that a given molecule will escape into the liquid phase. The process is statistical in nature, not deterministic. Even at the same temperature, different regions of the ice surface may behave differently depending on local imperfections, surface roughness, or even trapped air bubbles. This is why melting is not uniform, and why our intuitive explanations often fail. Feynman would point out that the visible melting is only a small part of the story. The true behavior of the system exists at a scale too small to see, governed by molecular motion and energy distribution. Another curious aspect is the role of energy in this process. Melting requires energy input, called latent heat. The salt does not provide energy, nor does it remove it. Instead, it changes the conditions under which energy is sufficient to allow water molecules to leave the solid lattice. When ice melts faster after salting, it is because the surrounding environment can now supply energy to the surface layer that remains liquid at lower temperatures. In extreme cold, however, there is insufficient thermal energy to allow any molecules to escape, and the ice remains frozen regardless of how much salt is added. Understanding this subtle interplay of energy and molecular structure requires thinking beyond everyday experience, which is why so many people assume that salt magically melts ice. The phenomenon also highlights the importance of systems and boundaries. Ice does not exist in isolation. Its behavior depends on the environment, air temperature, pressure, impurities, and the concentration of salt on its surface. When salt interacts with ice, it creates a local microenvironment, a thin layer of salty liquid water, whose properties differ from both the bulk ice and the surrounding air. This microenvironment is the stage where the physics unfolds. It demonstrates a general principle in science. Properties at the microscopic level can differ dramatically from macroscopic appearances. What seems simple, like ice melting, is actually the result of complex interactions at multiple scales. Feynman would also remind us to embrace uncertainty. Even with careful measurement, we cannot predict the exact path each water molecule will take. The system is probabilistic, and the melting process is best described statistically. Yet, this unpredictability does not mean we cannot understand it. Physics provides a framework to describe patterns, probabilities, and outcomes. The melting of ice with salt is a perfect example. By observing carefully and thinking critically, we can explain why it behaves the way it does, even though our first impressions might suggest otherwise. This teaches a broader lesson about science. The world is not always what it seems, and careful observation, combined with curiosity, allows us to uncover the hidden order behind familiar phenomena. To grasp the true nature of salt and ice, it helps to use analogies and thought experiments that make the invisible visible. Imagine standing beside a frozen lake and sprinkling salt on its surface. You expect instant puddles, yet sometimes nothing happens, or only a small area begins to melt. This isn't because salt has failed, but because the process depends on countless tiny interactions at the molecular level. Each water molecule is like a person in a crowded room, jiggling, moving, occasionally stepping into an open space. Salt molecules act like invisible guides, subtly influencing the behavior of those water molecules, lowering the threshold for motion, but never forcing it. The result is a statistical tendency toward melting, not a deterministic action. Now imagine another scenario, a thin layer of ice in a kitchen tray. Sprinkle salt on it, and within minutes the ice softens and small puddles form. In this controlled environment, conditions such as temperature, purity of water, and surface area allow the effect to be more visible. This demonstrates a crucial lesson from physics: context matters. The same salt can have drastically different effects depending on the environment. Nature operates through patterns of probability, not always through rules that produce the same outcome in every situation. Feynman loved these kinds of subtle puzzles because they force us to think beyond appearances and ask, what is really happening beneath the surface? Another way to understand it is to consider energy flows. Ice melting is not just a chemical or structural change. It is an energy process. Molecules in ice are held in place by bonds, and to escape into liquid, they need energy. Salt doesn't supply energy directly. Instead, it changes the balance at the interface, lowering the freezing point, so that the energy available in the environment is enough to allow molecules to break free. In other words, salt creates conditions that make melting more favorable without performing any action itself. This demonstrates a deeper principle in many natural phenomena. What seems like action is actually a shift in conditions that allows underlying processes to proceed more readily. Surface area, concentration, and temperature gradients also play a role. A large, uneven block of ice will melt more slowly than a thin layer because the interactions between salt and ice occur mostly at the surface. Microscopic impurities or roughness affect how quickly water molecules can escape, highlighting the importance of details that are invisible to the naked eye. Observing these subtleties requires careful measurement and attention, qualities that Feynman always emphasized. He insisted that understanding comes not from memorizing rules, but from exploring phenomena deeply and asking questions that challenge assumptions. Finally, this phenomenon encourages a shift in perspective. Humans tend to simplify what we observe, creating convenient stories that explain everyday experiences. Salt melts ice is one such story. It works in some contexts and fails in others, yet it obscures the underlying complexity. By studying the process carefully, we uncover a world of molecular motion, energy transfer, and statistical behavior. Even ordinary events can reveal profound truths about nature. Ice melting with salt is not just a winter problem or a kitchen experiment. It is a window into how the universe operates at scales we rarely perceive, reminding us that simplicity is often an illusion and reality is richer, more intricate, and far more fascinating than it first appears. As we reflect on the interaction between salt and ice, we begin to see that even the simplest phenomena are far more intricate than they appear. At first glance, ice melting under salt seems trivial, almost mundane. Yet, beneath that apparent simplicity lies a network of molecular motion, energy exchanges, and probabilistic behavior that most of us never notice. Every water molecule is jiggling, vibrating, and occasionally escaping the rigid lattice of ice, influenced subtly by ions in solution. Each drop of salty water on ice is an arena where thermodynamic laws play out quietly but precisely, demonstrating the hidden order behind what we often take for granted. Feynman would point out that this is the essence of physics, to uncover the rules that operate beneath our everyday experiences and reveal the beauty and logic of the universe. This process also teaches us about the limits of human intuition. Our senses and observations are imperfect guides to understanding the underlying mechanisms of nature. We see ice disappear and immediately conclude that salt melts it, yet the reality is far more nuanced. The microscopic interactions that govern melting depend on surface structure, temperature, concentration, and energy distribution. Even a small change in any of these factors can dramatically alter the outcome. Physics encourages us to look beyond appearances, to question assumptions, and to seek explanations that align with measurable phenomena rather than relying on convenient stories or oversimplified explanations. Curiosity, careful observation, and a willingness to embrace complexity are essential to uncovering the truths that the world quietly holds. Feynman often emphasized the joy of discovering hidden truths in everyday events. A common winter experiment, a block of ice with salt sprinkled on it, becomes a window into universal principles. The laws of thermodynamics, the concept of energy landscapes, the probabilistic nature of molecular motion, and the influence of microscopic variations all converge in a scenario that seems at first simple and ordinary. By studying it carefully, we gain not only scientific understanding, but also an appreciation for the subtle elegance that governs all natural systems. The seemingly mundane becomes extraordinary once we see the invisible forces at work, reminding us that the universe is richer and more intricate than our first impressions suggest. Ultimately, the lesson extends beyond ice and salt. It teaches us that reality is often more profound than it appears, and that the pursuit of understanding requires patience, observation, and a willingness to question what seems obvious. What we perceive is filtered through the limitations of our senses and our habitual ways of thinking. Science is a tool that expands our perception, allowing us to see the hidden structures that guide even the most familiar events. Ice melting under salt is no longer a simple kitchen experiment. It is a metaphor for the universe itself, a place where laws operate silently, patterns emerge from complexity, and beauty exists in the subtlety of processes invisible to the naked eye. By looking closely, asking questions, and refusing to accept simplistic explanations, we begin to experience a sense of wonder and humility that is at the heart of scientific inquiry. The next time you see salt melting ice, remember that you are witnessing more than a chemical reaction. You are seeing a microcosm of the natural world, a glimpse into the profound order that underlies apparent chaos. Feynman's insight reminds us that understanding, curiosity, and careful observation transform even ordinary phenomena into extraordinary lessons about reality, showing that the universe is far richer, more complex, and more fascinating than we often realize. To further understand the interaction between salt and ice, it is helpful to examine it through the lens of probability and molecular behavior. Each molecule of water in ice is held tightly in a lattice, but not uniformly. Surface molecules are less constrained, constantly vibrating and occasionally escaping into liquid form. Salt ions, when introduced, do not force these molecules to move. Instead, they change the statistical likelihood that a molecule will break free. The process is inherently probabilistic. No two molecules behave exactly the same way, and small variations at the microscopic level can lead to visible differences in how quickly ice melts. This probabilistic nature is a reminder that much of what we perceive as deterministic in everyday life is actually the result of countless small, random events governed by physical laws. This phenomenon also illustrates the importance of energy landscapes in physics. Each water molecule is in a potential well, held by bonds to its neighbors. To leave the lattice and become liquid, it must gain enough energy to overcome these bonds. Salt alters the local conditions, lowering the energy barrier at the ice surface and making it more likely for molecules to escape. The effect is subtle but cumulative. On a large scale, this is what we observe as melting. However, if the temperature is too low, the energy available in the environment is insufficient, and the ice remains solid. This demonstrates a key principle: conditions dictate outcomes in natural systems, and small changes can have significant effects. We can also consider the concept of microenvironments. When salt dissolves in the thin layer of water on the ice surface, it creates a locally concentrated solution. The properties of this microenvironment differ from those of the bulk ice or the surrounding air. This layer is where the action occurs, where molecules are more mobile, and where melting is initiated. Nature often operates in these microenvironments, and understanding them requires careful observation and measurement. Feynman would emphasize that such hidden layers of complexity are present everywhere. Even the seemingly simple act of ice melting under salt is governed by interactions that are invisible to the naked eye, yet they determine the outcome we observe. Another way to grasp this is through thought experiments. Imagine ice in different conditions: one block in a controlled warm environment, another in extreme cold, and a third sprinkled with different types of salts. The results vary widely, yet all obey the same underlying principles. This shows that our everyday language, saying, "Salt melts ice," obscures the true dynamics. The visible melting is merely the macroscopic manifestation of countless microscopic interactions, energy transfers, and probabilistic events. Science provides the framework to understand these interactions, but it requires moving beyond superficial explanations and embracing the complexity inherent in natural phenomena. Finally, this deeper perspective encourages a shift in thinking about observation itself. We often rely on intuition and direct perception to explain events, but nature is more subtle than appearances suggest. Ice melting is not just a simple reaction, it is an intricate interplay of energy, probability, and molecular behavior. Recognizing this changes how we approach science, teaching us to question assumptions, observe carefully, and appreciate the hidden order beneath everyday events. Even the most familiar phenomena contain layers of complexity that reveal the beauty and elegance of the natural world when examined with curiosity and precision. By seeing beyond appearances, we connect with the fundamental principles that govern all matter and energy. To see these concepts in action, consider simple experiments that reveal the hidden physics behind salt and ice. Take a block of ice and sprinkle table salt on one side while leaving the other untouched. Observe closely. The salted side begins to soften and form a thin layer of water faster than the unsalted side, but the difference is not instantaneous. The melting occurs gradually, driven by the interactions of molecules at the surface. The salt does not attack the ice. Instead, it alters the balance of energy, lowering the freezing point of water in the immediate vicinity. By watching this process unfold, we can begin to appreciate that even seemingly straightforward phenomena are governed by invisible forces and rules. If we vary the type of salt, the effect changes. Sodium chloride, calcium chloride, and magnesium chloride each interact differently with water molecules, producing slightly different freezing point depressions. This demonstrates that the microscopic properties of the solute are crucial. The behavior of the ice depends not only on the presence of salt, but also on the specific interactions between ions and water molecules. Such subtle differences reveal the complexity hidden in everyday events. Feynman would argue that paying attention to these details is where real understanding begins, not in accepting simplified statements or intuitive guesses. Another experiment is to use very cold ice, below the effective freezing point of the salt solution. Sprinkle salt and observe. Nothing happens. The ice remains solid because the environmental temperature is too low for surface molecules to gain enough energy to break free. This highlights an important principle: context matters. Salt does not melt ice in isolation. The surrounding conditions, energy availability, and molecular motion all influence the outcome. This demonstrates a broader lesson about nature. Phenomena depend on conditions, and the same intervention can lead to different results in different environments. It is a lesson in humility, showing that our intuition often fails when we oversimplify complex systems. Visualization tools, such as molecular models or animations, can make these invisible processes clearer. We can represent water molecules as tiny spheres connected in a lattice, vibrating and occasionally escaping when conditions are favorable. Adding salt ions introduces disruptions in this lattice, showing how the energy landscape changes. Such visualizations allow us to connect microscopic behavior to macroscopic observations, bridging the gap between what we see and what is actually happening. This is the kind of reasoning Feynman advocated, combining thought experiments, observation, and visualization to understand phenomena deeply. Finally, this exploration encourages a philosophical reflection rooted in science. Even a simple kitchen experiment is a microcosm of the universe's underlying order. It teaches that the visible world is shaped by countless invisible interactions, that energy and probability govern processes, and that careful observation can reveal hidden patterns. Ice melting under salt is not merely a practical phenomenon, it is a window into the principles that govern matter, energy, and motion. By examining it thoughtfully, we learn to see beyond appearances and recognize the intricate, elegant laws that structure reality itself. Science transforms ordinary experiences into profound insights, showing that curiosity and careful reasoning can reveal the extraordinary within the seemingly mundane. The story of salt and ice teaches us more than just a lesson in chemistry or physics. It teaches us about the way we perceive the world. We are accustomed to trusting our senses, but the visible melting of ice is only part of the reality. Beneath the surface, countless molecules are in motion, vibrating, breaking bonds, and interacting with dissolved ions. Each ion of salt subtly alters the behavior of water molecules at the ice surface, shifting the probabilities of movement and phase change. The process is not instantaneous, uniform, or deterministic. It unfolds as a dance of energy and motion on a scale far smaller than our eyes can detect. Observing it carefully allows us to glimpse the hidden order that governs all physical systems. Consider how easily humans simplify this phenomenon. We say, salt melts ice, because that explanation is convenient, intuitive, and seems to match what we see. Yet the truth is richer. Salt lowers the freezing point of water. Surface molecules gain energy, and only under favorable conditions does melting occur. The difference between what we perceive and what actually happens is a recurring theme in science. Nature operates independently of our assumptions and expectations. Feynman emphasized that understanding comes from examining phenomena closely, performing experiments, and questioning assumptions rather than relying on simplified stories. In this context, the melting of ice under salt becomes a case study in scientific humility and rigor. This phenomenon also illustrates the importance of context. Environmental conditions, surface structure, temperature gradients, and even microscopic impurities all influence how ice responds to salt. Two blocks of ice, seemingly identical, can behave differently when treated the same way. This variability demonstrates that natural processes are not purely mechanical in the way everyday intuition suggests. They are probabilistic and context-dependent. Understanding these subtleties requires observation, measurement, and reasoning at multiple scales. The surface layer of ice, only a few molecules thick, is the arena where physics operates, and what happens there determines the larger outcome. Such insights encourage us to look beyond appearances and recognize the layered complexity of the natural world. Visualizing this process strengthens understanding. Imagine ice as a lattice of vibrating spheres, each representing a water molecule. Salt ions are scattered among them, disrupting the order and changing the local environment. The energy landscape shifts, allowing some molecules to escape into the liquid state. Each movement is random, yet patterns emerge statistically. Observing melting in real life, or through molecular animations, helps bridge the gap between what we see and what is truly happening. Science allows us to map the invisible, transforming the mundane act of ice melting into a window into molecular dynamics, thermodynamics, and probability. Finally, this exploration leads to a deeper reflection on reality. Even ordinary phenomena conceal extraordinary complexity. Ice melting under salt is a metaphor for the universe. What appears simple often hides intricate processes, energy flows, and statistical interactions. By studying it, we train ourselves to question assumptions, appreciate subtlety, and cultivate curiosity. The lesson extends beyond ice. Careful observation, thoughtful experimentation, and openness to complexity are the tools by which we uncover truth in nature. Feynman's insight reminds us that the universe operates by elegant, sometimes hidden principles, and that curiosity, attention, and reasoning allow us to discover these principles even in the most familiar surroundings.